Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome back to The Explainer. I am absolutely thrilled to have you here today. You know, if you're a focused learner who really wants to grasp the inner workings of modern networks, well, you are in exactly the right place. Today, we're focusing our lens on ITN Module 7, Ethernet switching. We're going to break down exactly what happens under the hood of a network switch. We'll explore how these devices manage the incredible chaos of network traffic and turn it into this beautifully streamlined, high-speed flow of data. Picture a massively busy intersection in a major city. Now imagine there are no traffic lights, absolutely no stop signs, and literally everyone is trying to cross at the exact same time. That's kind of what early networking looked like. It was pure chaos. But today, billions of devices communicate seamlessly. So how in the world do millions of data frames cross a network without ever colliding? That's the central problem that a modern network switch solves. And by the end of this explainer, you're going to understand exactly how it pulls off this incredible feat. All right, here's our roadmap for today. We'll hit 1, the magic of Ethernet, 2, anatomy of a frame, 3, building the MAC table, 4, the forwarding decision, and 5, speed versus reliability. Let's kick things off with section 1, the magic of Ethernet. Okay, let's dive into this by contrasting our past with our present. In legacy Ethernet, networks use these devices called hubs. And hubs were basically just repeaters. If a signal came in one port, the hub just blindly copied it and blasted it out of literally every other port. Because everyone shared the same physical medium, devices had to operate in half-duplex. That means they could only send or receive, but never both at the same time. If two devices sent data simultaneously, bam, you got a collision and the data was totally destroyed. Now look at modern Ethernet. Switches changed the game completely. A modern switch operates in full duplex, meaning devices can send and receive at the exact same time. It isolates every single port into its own dedicated collision domain. The result? 0 collisions. It is a brilliantly efficient system. Moving right along to section 2, anatomy of a frame. And this brilliantly illustrates the essential components tucked inside that data payload. When a device wants to send an IP packet, it encapsulates it inside this layer 2 Ethernet frame. Notice the front of the frame here. Right after the preamble, we've got the destination MAC address, followed immediately by the source MAC address. This is absolutely crucial sorting information. The switch reads this header first. Then, take a look all the way at the tail end of the frame. That's the FCS checksum, or frame check sequence. It's basically a mathematical value calculated by the sender. The receiving switch recalculates this exact value to see if the frame was corrupted or damaged during transmission. So it's kind of like a built-in quality control mechanism. Now, we just saw MAC addresses in that frame header, but let's take a second to define exactly what they are. A MAC address, which stands for Media Access Control Address, is a 48-bit address, typically expressed as 12 hexadecimal digits. You can really think of this as the permanent physical fingerprint of a network interface card. While an IP address might change depending on, what network you connect to, the MAC address is the core unchangeable identifier that the switch uses at layer 2 to make all of its high-speed sorting decisions. Which brings us perfectly to section 3, building the MAC table. So, if the switch relies on MAC addresses to sort traffic, how does it actually know where they are? Unlike a legacy hub that just shouts everything out of every port, a switch acts as an intelligent traffic cop. Or better yet, think of it as a lightning-fast postal sorting facility. It actively records where every single package comes from. When a switch is first powered on, its memory, specifically its content addressable memory or CAM table, is completely empty. It literally has to learn the layout of the network dynamically, just by listening to the traffic that enters its ports. Now, what's really interesting about looking at this actual command line output from a Cisco switch is exactly how it builds that map. Someone typed the command show MAC address table. Look closely at those rows marked dynamic. The switch actually examined incoming frames, read the source MAC addresses, and mapped them directly to specific physical ports, like fast Ethernet 0/1, 0/5, and 0/13. It learned all of this automatically. And here's a fun fact. By default, if a switch doesn't hear from a MAC address for 5 minutes, it'll just age that entry out and wipe it from the table. That keeps its memory fresh and accurate. All right, let's look at section 4, the forwarding decision. The switch performs a very strict, incredibly fast 2-step process for every single frame it processes. Step 1 is the learning phase. The switch looks at the source MAC address of the incoming frame. It checks its table. If the address isn't there, it adds it along with the incoming port number. If it is there, it simply resets that 5-minute aging timer we just talked about. Easy enough, right? Then comes step 2, the forwarding phase. Now the switch looks at the destination MAC address. If it finds a match in its table, it forwards the frame out of that one specific single port. It's incredibly efficient. But wait, what happens if the destination MAC address isn't in the table yet?
So the crucial point is how the switch handles that exact blind spot. We call this an unknown unicast. If the switch searches its MAC table and cannot find the destination address, it doesn't just drop the frame. No way. Instead, it guarantees delivery by flooding the frame out of all active ports, except for the port the frame just came in on. The logic here is actually super simple. If you don't know where the destination is, just send it everywhere. The correct device will receive it, process it, and when it replies, the switch will read the source MAC of that reply and finally learn where that device is located for next time. Pretty smart, right?
This takes us to our final section, Section 5, Speed versus Reliability. We've talked a lot about how a switch decides where to send a frame. Now let's contrast the two primary methods for how it physically moves that data. First up, we have store and forward. In this method, the switch receives the entire frame, literally all the way to the end, and computes that FCS checksum we saw earlier. If the frame is corrupted, it just drops it. This prevents bad data from wasting your network bandwidth. Now, because it waits for the whole frame, latency is slightly higher. However, this method is absolutely required if your network uses quality of service, or QoS. For instance, if you want to prioritize voice-over IP phone calls over standard web browsing, the switch must use store and forward. On the other hand, we have cut-through switching. Here, the switch acts immediately. It buffers just enough of the frame to read the destination MAC address and then instantly starts pushing the bits out the correct port. It completely skips the FCS check. This means ultra-low latency for sure, but it also means corrupt frames might accidentally get forwarded. Let's move to and see how this builds, because cut-through switching actually breaks down into two specific subcategories. The first is fast-forward switching. This is the absolute lowest latency possible. The switch reads the destination MAC address and immediately fires the frame out the exit port. But again, it might forward bad packets. The second variant is a really clever compromise called fragment-free switching. See, in early Ethernet, the vast majority of collisions and errors happen during the first 64 bytes of transmission. This created these tiny, broken frames called runts. So fragment-free switching waits to receive just the first 64 bytes to ensure a collision hasn't occurred, and then it immediately starts forwarding. It's essentially a perfect middle ground between high speed and basic error checking.
Wow, we've covered incredible ground today. We started with the sheer chaos of legacy hubs, zoomed all the way into the microscopic structure of an Ethernet frame, learned how a switch brilliantly builds its dynamic MAC table, and explored the exact logistical decisions it makes in literally microseconds to balance speed and reliability. By keeping data flowing so efficiently at the local level, switches really are the unsung heroes of our modern infrastructure. But this brings up a fascinating thought to leave you with. If switches are doing all this high-speed sorting at Layer 2 based on physical MAC addresses, how do these rapid Layer 2 switching decisions impact the broader global routing of IP addresses up on Layer 3? Think about how routers and switches have to work together to pass your data across the entire world. It's like a giant puzzle. I really hope this explainer gave you a rock-solid understanding of Ethernet switching. Thank you so much for learning with me today, and as always, stay curious.
Thank you for watching. See you in the next episode.